Thank you. I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you help us to use this time wisely, Lord, and glorify you what we do. In your name I pray, Lord Jesus. Amen. So, I had a... Oh, hey.
I didn't get your email.
Oh, I didn't send... Oh, Stephen didn't send you one either?
I didn't get one from Jim either.
Okay, when I'm...
Yeah, no, just one.
I will... I'll send you one as soon as between classes here.
Yeah, no problem.
Yep.
Farewell.
All right, so we're on... my goodness, what lecture are we on? 30?
31. I don't know. It might be 30. I thought it was 31. We didn't have a lecture number.
So let's say lecture...
Last one I remember is 29.
So... So today, man, Dr. Sprano's a really bad influence. I had no idea. All right. So I am ignoring Galilean as a definition. And you're saying, but didn't you already type up all the definitions from the next two chapters of Galilean? I did do that. I regret that. And some of those definitions are still relevant, but I'm going to follow for this lecture and the next. I'm following Fraleigh. I will post the relevant chapters in Blackboard sometime soon. Okay, so here it is. A field. I mean, there's a significant overlap between what I'm using and Galilean. So if you've already read Galilean, it's not a waste of your time. A field, E, is an extension field. An extension field of F, of a field F, if F is, and we'll use this notation for subfield, okay? If F is a subfield of E, all right. So all that means, right, is that E is some larger field such that F appears inside it, and it is a field with respect to the operations in E. This is an extension field. So here's a picture people like to draw. Complex, real, rational, and so this is a so-called tower of fields. To be more specific, so, R is an extension field of Q, and C is an extension field of R. All right? I mean, while we're at it, C is also an extension field of the rationals. Right? So this is the notion of an extension field. So, here's the fundamental theorem. This theorem is due to Kronecker. But the proof we give is not due to Kronecker. The proof we give is born of a few more decades of mathematical progress. I mean, Kronecker wrote down this theorem before all of the theory we'll use to prove it was developed in its entirety, I suppose. Here it is anyway. Let F be a field. All right. And f of x, a non-constant polynomial, in f of x. Then there exists an extension field E of f and an alpha in E all right, such that f of alpha is equal to 0. So what this is saying is that, suppose you have a polynomial, right? And you can't find any zeros for it in your favorite set of numbers, all right? Assuming those numbers form a field, like rational numbers or real numbers. Well, guess what? You can make up a new field called an extension field. And in that new field, this polynomial will have a 0. All right? That's what the theorem says. The proof goes like this. F of x has an irreducible factor. P of x, how do I know that? By our previous work on polynomials, right? Polynomials over a field form a unique factorization domain, which means any polynomial can be factored into a product of irreducibles. We don't even need all that. The fact that it contains one irreducible suffices. So the fact that, polynomials over a field of a unique factorization domain, part of that is that every polynomial has an irreducible factor. All right? So you can let E be equal to f of x mod the ideal generated by P of x. Note, P of x irreducible implies that the ideal generated by P of x is maximal. Proved that before, right? And then, so what are you looking at? You're looking at a ring mod a maximal ideal. Remember, a few lectures back, we proved that that was a field, right? Ring mod a maximal ideal is a field. One of our fundamental theorems in ring theory. So that implies that E is a field. Okay, so it's a field. We got that. Now what we need to do is to find this element I claim. For a couple things, right? We need to show what? It contains f as a subfield too, I suppose. So to do that, consider this. If we let psi be a mapping from f to this to E, right? By psi of A equals to A plus P of x, right? You can prove that that's a, well, it's not an isomorphism, but you can prove that it's an injection. Let's see here. So, let's see here. You can prove it's a homomorphism at least. How about, for example, psi of A times B is equal to what? I might be doing one of your homework problems right now. I'm sorry if I am. Did I assign number 33 from chapter 17? Or are we past that? We might be past that. I don't know. One of the homework problems is to prove that this contains a subfield which is isomorphic to F, which is what I'm currently engaged in. All right. Anyway, so clearly this is a homomorphism by the definition of multiplication of cosets, right? And also what? All right. Well, it's also additive. So let's see here. Getting to the point. My point is just that things of this form, like a constant plus the ideal generated by P of x, those essentially give you a copy of the field F inside this extension field, right? So in that sense, so if we identify A with A plus P of x in E, it gives. Now, I would say it really gives F tilde is a subfield of E, where F tilde is equal to the image of F under this mapping psi. All right. So, I mean, technically, if you want to be really picky, this E I've constructed isn't strictly speaking, but no one cares about this. Like, when we say that E is an extension of F, usually people are content to say there exists some isomorphic copy of F, say F tilde, and F tilde is a subfield of the extension field. So here, the copy of F that's in this set of objects is just A plus the coset. It's just that sort of thing. Constant polynomials, really. Modulo the that. Okay, I'm going to stop. So there's our copy of F inside this thing. And what's next? We need to show that there's this alpha. So we'll let alpha equal to x plus the ideal generated by p of x, all right? That's an element of E, right? And what I want to show to you now is that if we look at phi alpha of p of x, what's that? Remember, I'm using some, this is the evaluation homomorphism. So in other words, I plug in, I need to give some more details here. So p of x, let's let it have the form a n x to the n plus a n minus 1 x to the n minus 1 plus dot 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 plus a2x, let's say a1x plus a naught. All right, so again, this is an element of the polynomial over the field F. And so we defined the evaluation homomorphism. What did we do? We took the polynomial and we replaced x with alpha to the power of x in each slot, right? That was the evaluation homomorphism. So this is equal to, an alpha to the n plus an minus 1 alpha to the n minus 1 plus dot 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 plus a1 alpha plus a naught by definition of the evaluation homomorphism. And by the way, this is what we call p of alpha, right? I mean, that's what p of alpha means. All right? I want to show that that's 0. So let me just do a little side calculation here. What's alpha to the n? That's x plus the ideal generated by p of x raised to the power n. How does that work? That works as x to the n, like that, right? That's how when you power in the coset, it just powers the representative, right? And that's going to be true for n minus 1, all the way on down the chain, right? So, I mean, I can just as well replace the n with a j, And this, I mean, that would have been smarter, right? J equals to 1, 2, 3, all the way out to n. So what's that give us here? That gives us an x to the n plus p of x, right? Plus an minus 1 x to the n minus 1 plus the ideal p of x, right? Just this element. Dot, 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 dot. And I'll continue down here. A1x plus p of x plus a naught, all right? Now this a naught, it bothers me. I feel like you should really say, to be more honest here, it's really a naught plus p of x. I mean, that's really what we're doing. Anyway. So I'm going to add that because the books don't seem to add it, but I don't know, my part of me that wants to write too much wants to write that there, so I'm going to write it. All right, giving into my more base urges. Let's see here. So how do you add cosets? You add representatives, right? So we've got an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a naught, all of that plus p of x. But what is that? That's p of x, right? So this is just equal to the ideal generated by P of x, aka 0 in this quotient, right? And there you have it. P of alpha is 0. In the quotient of f of x by the ideal generated by P of x, x serves as the 0 of P of x. This is really not surprising if you start to gain an intuition for these things, because when we form a quotient by the ideal generated by P of x, what are we doing? I mean, our intuition for this should be that we're making a new 0, right? We're saying everything in this ideal generated by P of x serves as 0 in the quotient, right? So of course the polynomial P of x has a 0 in this quotient. It's just x. But for notational, so we don't go nuts and use x like 13 different ways from Sunday, we'll introduce a new symbol, alpha, and say alpha is equal to that. That makes us, you can see better the logic here if we introduce that notation. That's why I do. Okay. Let me erase something here. I wrapped up what I had to say about chapter 18 yesterday in the help session, and I will post that for you guys to watch at your leisure. Basically, I just wrap up, chapter 18 of Galilean, and to summarize, all I proved in that little snippet was that, in fact, every principal ideal domain is a unique factorization domain. It uses something called the extending chain condition to prove this. It's very beautiful mathematics. Took us about 15 minutes to walk through it. I've already typed it up in the notes there for you to look at. It's also in Galilean. I really just reproduced the argument in Galilean. And the takeaway message from that chapter is that we've got these three different kinds of rings to look at. We've got, Euclidean domains, principal ideal domains, and unique factorization domains. These are inequivalent notions, but they are related. Every Euclidean domain is also a principal ideal domain. That's an implication we proved. And also every principal ideal domain is a unique factorization domain. That I proved yesterday in the help session, and it's at the end of chapter 18 in Galilean. And then the converse direction doesn't work. There are unique factorization domains which are not principal ideal domains, and there are also Euclidean domains which are not principal ideal domains. I only hold you responsible for the counterexample of the unique factorization domain, which is not a principal ideal domain. The central go-to example there is just polynomials with integer coefficients. We've seen it before. If you look at the ideal of polynomials with even constant coefficients, that's an ideal which is not principal in z of x. So z of x is not a principal ideal domain. There it has an ideal which is not principal. And yet it's a unique factorization domain. You can take any polynomial with integer coefficients and factor it into a up to associates unique and reordering unique product of irreducibles. I do not hold you responsible for the counterexample of something that's the Euclidean domain, something that's a principal ideal domain, but wait a minute, another way around. Something that's Euclidean domain but not a principal ideal domain. There is, to my knowledge, no easy example of that. So anyway. There's no example in Galilean. There's part of your hint. But anyway, he gives a reference to some paper from the 40s. Okay, so I'll do an example here. If we look at f equal to the rationals, and f of x equal to x to the fourth minus 5x squared plus 6, all right? Then this factors, right? This is reducible, and it reduces to what? X squared minus 2, right? X squared minus 3, I believe. Right? So this quartic happens to not be irreducible. It's reducible. There's reduction. But of course these, x squared minus 2 and x squared minus 3 are both irreducible over q. So he says we can construct an extension field to Q, right, with 0 for x squared minus 2, what do you do? How about E equals to Q of x mod what? Right? That has a 0 for x squared minus 2 by Kronecker's theorem. All right. So in here, this has alpha such that what? Alpha and E such that what? Alpha squared minus 2 equals a 0. Right. The notation for this is called Q square root of 2. Now, of course, you can also do, likewise, if we take Q of x, right, and we mod by x squared minus 3, what would that give you? That has beta such that what? Beta squared minus 3 equals to 0. By Kronecker's theorem, there exists a beta. The beta actually, what is the beta in this set? I mean, the thing that's actually beta is just x plus the coset x squared minus 3 in there. That's actually what is beta. Serves as the beta. But, well, anyway. Okay, so definition. An element alpha of an extension field E of a field F is algebraic, all right, over algebraic over F if f of alpha is equal to 0 for some non-zero f of x in the polynomials over f. Now, otherwise, what do we say? Is a transcendental. Transcendental well, I'll just say is transcendental over F. All right, so let's do some kind of stupid stuff. So let's think about this. If C is an element of F, right? Then C is algebraic over F, right? It's kind of stupid. Think of F as its own extension field. What polynomial, what non-zero polynomial takes C as a 0? How do you get C as a 0 of a polynomial? X squared minus C. You're thinking too hard. How about just x minus C? C is a 0, right? So every real number is algebraic over the reals. Okay, not that surprising. Example, let's do something a little bit more exciting. If you look at alpha equals to I, right, in how to say this? In C, right? Yeah, duh. Complex numbers. This is algebraic over the reals. Why? How about this? F of x equal to x squared plus 1 has f of I equal to I squared plus 1, right? Which is minus 1 plus 1, which is 0, right? By the way, of course, we can explicitly build the complex numbers using Kronecker's theorem, right? I mean, side comment. And we did this another day already, right? It's not new for us in here. If we take, hey, oh well, that one's really dry. Maybe I've hit a student on the ricochet though, I don't know. Let's see here, at least their feet. So if you look at R of x mod x squared plus 1, right? This is a field in which, you know, this looks like what? This is basically a plus bx plus this thing. A and b are real numbers. So if you call alpha, quote unquote, right, x plus this, then you can rewrite this as a plus b alpha, such that a and b are real numbers. But by the way, alpha squared is what? In this notation, alpha squared is minus 1. So, I mean, Kronecker's theorem gives us a natural way of constructing the complex numbers by a quotient of real polynomials by x squared plus 1. In some sense, x is the minus, I mean, x is serving the role of the square root of minus 1 of I in this set. I was working with Nathan this summer. He insists on using the notation. This is Nathan's notation. I'm not sure I buy into it, but it does serve its purpose. Like, this is what Nathan insists on writing in this place of what I wrote. You take all formal polynomials in I, and you mod by I squared plus 1. That makes I squared equal to minus 1, and that makes polynomials in I into complex numbers. This is his notation. It's an efficient notation. I like it. But anyway, so I is algebraic, right? Now, what's not algebraic? Pi is not algebraic over the rationals. Of course, pi is algebraic over the reals, right? E.g., I mean, x minus pi, f of x equals x minus pi does it for you, right? But to say that pi was algebraic over the rationals would mean that I could find a polynomial with rational coefficients which had pi as a 0. That is in fact impossible. I'm also not going to prove that today. If you can prove that today on your own, somebody probably should give you a doctorate in mathematics. Like that's not, it's not an easy one. You get a jersey in convo. This is one of the great aspects of my linear algebra teacher. Well, first of all, I had linear algebra over the summer, mostly with computer science majors at Appalachian. and the guy who's teaching it, he'd wear like a polo shirt, and like he'd reach up on the board to write, and like, you know, his belly would show like a little bit. It was really chill, like this course. And he used to throw out these little comments like, if you can show this, you know, you should get an A on the next test, or I should give you an A on the course. You should get an honorary degree and you know, a paid position at a university. I mean, he had varying degrees of difficulty for different things. It was fun. It's fun. Okay, so a more interesting example of a number which is algebraic, and this is I'm going to work backwards here to show you why it's algebraic. So take alpha equal to the square root of 1 plus the square root of 3. This is algebraic over the rationals. You're like, and you should notice something here. Asking if a number is algebraic without saying with respect to which field isn't particularly useful, is it? Like, this number is automatically algebraic with respect to the reals. It's a real number. X minus it gives you, again, okay, I've said that enough. But this is algebraic over Q. That's less obvious. How do you do it? Work backwards, basically. So alpha squared is what? So this is kind of scratch work, all right? So then alpha squared minus 1 is root 3, right? And then alpha squared minus 1 squared is 3, aka alpha to the 4th minus 2 alpha squared plus 1 equals to 3, also known as alpha to the 4th minus 2 alpha squared minus 2 is equal to 0. So we should look at f of x equal to x to the 4th minus 2x squared minus 2. That polynomial with rational coefficients takes alpha as a 0. Moreover, I can tell you that Q mod x to the 4th minus 2x squared minus 2 is the extension field, of x, is the extension field of the rationals in which that happens, right? This is also denoted Q adjoin alpha. How do I know that I can mod by that and get a field, by the way? It's not immediately obvious that a quartic is irreducible over the rationals, is it? This is the simple extension by alpha. We're just adjoining one thing to the field that we're given. So can you guys tell me? Eisenstein. Can you guys tell me? 2. 0. Oh, I'm sorry, I was sneezing. I'm sorry. No, I mean Eisenstein by 2, right? It's irreducible. So that means that being irreducible, this is a prime ideal, hence maximal, hence that's a field, and that's the extension field, which has that wacky number in it, right? Okay, so that. So, theorem. Well, actually, I don't care much about. The next theorem here tells us that it gives us a criteria for when the element is transcendental. So I'm gonna go ahead here. Here's what I want. Let me. theorem and extend let E be an extension field of F, all right, and alpha in E, alpha algebraic over F, right? Then there exists an irreducible polynomial P of x in F of x, all right, such that P of alpha equals to 0. This irreducible polynomial P of x is uniquely determined all right, up to a constant factor in F. And is a polynomial of minimal degree. Greater than or equal to 1 in F of x, having alpha as a 0. If f of alpha equals to 0 for f of x in polynomials over f, with f of x being a non-zero polynomial, then p of x divides f of x. Yeah. I'm probably going to regret erasing this. Definition. Let E be an extension of F, alpha an element of E algebraic over F, the unique monic P of x described in theorem 29.13, which is this one. Hey, that seems about right. Chapter a day. So we're in chapter 29 of Fraleigh, more or less. That's about right. Let's see here. His chapters must be shorter, or sections. Some of Galeon's chapters take more than a day. We've experienced this. Unique, monic, irreducible, such that what? It's the unique, monic, irreducible P of x for which P of alpha is equal to 0. All right. We will denote this by, here you go, IRR alpha if, I don't know, I have, anyway, it's the irreducible polynomial for alpha over f. Or if, all right, so the degree of alpha, the degree of this thing is the degree. That's the degree of alpha over f. All right. So let's see here. The thing I just erased and I regret erasing basically showed that the irreducible polynomial for the thing 1 plus root 3, right, over the rationals, what was it? X to the fourth, just a second, see if I remember, minus 2x squared minus 2. Don't ask me the middle name of my children. It's been replaced by that. Hope you guys are happy. Okay, it's true. I'm not sure I knew it before that actually either. Also, wait a minute. I forgot to turn off the camera. Oops, let's see here. No, oops. What's the degree of this element? This is a degree 4 element. So this algebraic number over the rationals, the square root of 1 plus the square root of 3 it's an algebraic number, and it has degree 4 over the rationals. Okay. So this simple extension, right, that I'm talking about over here, I mean, in the case that it's algebraic, it's pretty, we can wrap our minds around that pretty concretely. All right, like, here's a theorem. If E is simple extension of F, in other words, F is equal to, E is equal to F alpha, where the degree of the irreducible polynomial of alpha over F, all right, is equal to n, which is greater than or equal to 1, then each beta in the extension can be uniquely expressed. And by the way, guys, this is the theorem you've been waiting for. This one finally will give you a better sense of what in the world we're talking about here. Can be uniquely expressed. That's why I wanted to get to it today. As beta, I don't know, at least I feel more calm once I write this theorem. B1 alpha, B2 alpha squared plus plus Bn minus 1 alpha to the n minus 1. This is his theorem 29.18. So we've already seen this at work. Like complex numbers, right? What's the degree of the extension of the complex numbers over the reals? It's a degree 2 extension, right? So the irreducible polynomial for the complex number I is x squared plus 1. It's a degree 2 extension, right? Any complex number can be expressed as a plus bi. That's because it's a degree 2 extension. If you're working in some context where you're looking at an extension field where your element has degree 4, like this thing here, what is this? Calling this thing alpha for a second here. So Q adjoin alpha, what's it look like? This theorem tells us, without further calculation, I know what it looks like. It's A plus B alpha plus C alpha squared plus D alpha cubed, such that A, B, C, D, rational. And that's the field. That's what this theorem says. Once you know the degree, if you're at least, well, I mean, okay, fine. If it's not a simple extension, then there's more to say. All right, that's what Friday is actually about. What happens when it's not a simple extension? When you join more than one thing, how does it work? That's what we're talking about Friday. But when you just adjoin one thing, then essentially it just forms a vector space, right? This is a vector space of dimension n over the field F, where the basis for the vector space is simply given by 1 alpha, alpha squared, alpha to the n minus 1. That's all it is. Just like the complex numbers are a vector space of dimension 2 over the reals, with basis 1 and I. This is a vector space of dimension 4 over the rationals, with basis 1 alpha, alpha squared, alpha cubed. And the rules for multiplying alpha are kind of wacky, right? They're governed by this rather weird equation, alpha to the 4th minus 2 alpha squared minus 2 equal to 0. So when you multiply things in here, you got to do it with respect to that. Right? It's weird, but you can do it. The proofs that I have skipped, namely this one and that one, are really simple. And they involve things we've already talked about. And they're about a half a page. And I could have easily spent all our time on that, but I decided not to. So, depending on how I read the room, Friday or Monday, I may go back and do those proofs after break. But I thought we should focus on the examples and the ideas before break, at least. Let's see here, another example. Eraser. Oh, yeah. By the way, the reason I'm using Fraleigh instead of Galilean here is to make it easier on you guys. There is some stuff in Galilean which is fine, but I don't want to go quite that far into field theory. These two chapters that we're covering in Fraleigh are much more focused in on what I want you guys to know for this course. The other things that are in Galilean, there's things on splitting fields, perfect fields, fancier stuff. Part of that leads into the next chapter I wasn't covering. And, we can cover whatever we need to of that in the next course. And I just want to make sure that most of you guys have the basic ideas about extension fields and how we can construct numbers with extension fields. I think that's what's so interesting, is this gives us a rather simple prescription for constructing complex numbers from real numbers, right? I think that's really neat, personally. And also, these are weirder things, right? Like, this is a number system that has rational numbers and this thing. That's kind of cool, right? There's something else you can do. You can take the rational numbers and you can throw in like all possible algebraic numbers. What's an algebraic number? I think I defined it here, right? Well, not there. I guess I erased it. Algebraic number is just one for which, there is some polynomial in the rationals which takes it as a 0, right? Not all numbers are algebraic. Pi, e, natural log of 2, stuff like that, right? Not algebraic. But if you think about how many algebraic numbers are out there, well, there's a lot of them, right? One of the things you can prove about algebraic numbers is that they're countable. So in other words, the cardinality of the algebraic numbers is still the same as the cardinality of Q, which is the same as the cardinality of the natural numbers. That means there exists a bijection from the natural numbers to this awful set of all possible algebraic numbers. Don't ask me for that bijection. That's like Dr. Sprano's department. He can give you these kinds of bijections. It's his business. But let me see here. Another example. Where am I? Example 6. Oh, thank you. Here he looks at p of x equal to x squared plus x plus 1 in z2x. Is that irreducible? You see here, he looks at r of x. Oh, r of x, listen to me. Oh, anyway, I think I'm out of time, so I'll shut up. But there's a great example here, example 29.19. He gives us an example of a finite field with 4 elements, which is built from taking a quotient of polynomials over Z2 with something simple. So. I'm posting these. Yeah, I scanned both chapters. I'll post them here in a minute, so you guys can read along. I do also hope to finish my notes, but